people, but you also long to understand climate and environmental forcings. And we are incredibly fortunate to have Jane Baldwin on the CLASH steering committee. Jane is an assistant professor at the University of California, Irvine. She works on atmospheric dynamics and how those affect climate and extreme events. And we're going to hear about storms, fires, all kinds of things. And Jane, thank you so much for being here. And go ahead and kick it away. I will mention really quick, if you're just joining us, please be aware that the talks are all back to back to back to back. And at the end of the talks, we will have this dedicated period for Q&A. However, please input your questions in the meantime into the Zoom chat or in the Google document that's going to be posted periodically throughout the session. So keep your brains rolling and otherwise save the discussion for the end. But Jane, all for you. Thanks.
Okay, great. Thanks so much for the kind introduction, Josh, and it's really great to be here this morning. So as Josh mentioned, I'm running the climate and environmental forcing session. I'm an atmospheric scientist and climate modeler, and so I'm going to start things off with a pretty broad overview of climate models and the kind of outputs they produce and various methods for downscaling them to produce higher temporal and spatial resolution outputs that might be of more direct interest for land surface hazards. Then we're going to go into a presentation by Amir Aghakouchak, who's also a professor at UCI. I'm talking about, who's really an expert on compound and cascading hazards, and he'll be talking about those particularly from kind of a climate change angle. And then Park Williams will be discussing different methods for modeling how forest fire is changing. Chuxuan Li will look at an augmentation of WRF-Hydro to simulate post-fire debris flow. And then Deanna Nash will close us off examining modeling atmospheric rivers associated with hazards in Southeast Alaska. So the focus of this session, I've tried to make it, we're going to start out with thinking about different ways of just modeling climate and environmental forcing, and then we're going to move into methods, basically ways people have tried to merge these forcings with land surface hazards. Again, this is just a reminder of the key questions we're hoping people can focus on. If you're trying to come up with questions, please target these types of areas too, thinking about different model couplings, modeling areas that need attention, and also types of data we need to support these models, and friendly reminder that this session will be recorded. Okay, so I'm going to start things off by showing a cartoon I show when I give outreach talks about climate modeling, simply to make the point that, you know, in many types of science, you think about like biology, you can create, say, an experimental mouse with a different gene and just breed many, many more of that experimental mouse or fly or whatever and figure out some statistically significant effect. Unfortunately, in the case of the Earth, we just have one Earth and we can't go around producing many additional true Earths. So instead, we've developed pretty sophisticated numerical models that we hope can simulate kind of the most important processes in the climate system, and then will allow us to learn something about the climate system and how it's changing with warming or under the influence of other types of forcings. So 3D climate models are called general circulation models, or sometimes or abbreviated as GCMs. Sometimes you'll also see them called global climate models, which conveniently also is abbreviated as GCM. Basically, these models take the Earth and break it up into a bunch of grid boxes and use the Navier-Stokes equations, which govern fluid flow on a rotating sphere, to step forward the circulation of the atmosphere and the ocean in time. And using this method, you can do quite a good job of simulating the large-scale aspects of the circulation of the atmosphere and ocean. This same kind of strategy underlies weather prediction. If you run the models for longer with slightly different types of boundary conditions and structures, you can use them to simulate many years of data, so get a sense of climate. So the typical resolution of these global climate models tends to be 50 to 200 kilometers. Really, something like 100 to 200 kilometers is more typical. And when you're getting to 50 or 25 kilometers, that's like a really high resolution model and very computationally intensive. As a result, there are many processes that are important for the climate system that can't be explicitly simulated using these models. And some of these processes include things like clouds, aspects of hydrology, vegetation, and there are aspects of climate models that basically create subgrid scale parameterizations to represent these processes because they do matter for climate. Now, things you can do with a climate model. So first, you need to expend a lot of computational power to run these things. Most of them are run on federal supercomputers. Sometimes you'll see them being run at universities, but these days, more and more of the time, they're run on these shared supercomputing resources. This is something I like to do in my research is run idealized experiments, which I like to describe as playing God, where you say, take a mountain range, flatten it, and see how rainfall patterns across the Earth change. This is really for understanding sort of more fundamental climate dynamics questions. But you can also use these models in more of a projection or prediction mode where you basically force the model with different scenarios of increasing greenhouse gases to understand how temperature and other aspects of weather and climate might change with, say, global warming, for example, or maybe changes in aerosols or other things that we expect to vary over time. You also see studies looking at land use change, for example. So this is a plot from an IPCC report just showing for two different suites of models, one forced with a higher emission scenario and a lower emission scenario, that the temperature of the planets diverge. So one of the, a key thing to understand about these simulations is that there obviously is a lot of uncertainty in future climate projection, but we actually understand the sources of uncertainty, and climate models can be used to sort of understand and quantify the different sources of uncertainty. So this is a plot showing changes in temperature going into the future. This is from the IPCC AR5. You see very similar plots in the IPCC AR6 as well. And one of the main things you can get a sense of is that over the next 15 years, the dominant source of uncertainty in our projections is internal variability, so the natural variability of the climate system. Over the next 15 to 50 years, the dominant source of uncertainty becomes model spread, which is basically uncertainty in our scientific understanding in different model structures. And then over the next 50 to 100 plus years, this is when RCP scenario spread, which is really how much emissions are we going to emit into the future comes to the fore. Now, I just want to give some nuts and bolts information about climate model outputs and publicly available simulations to help stimulate thinking about how these might be coupled to land surface hazard processes. So the types of outputs you have from climate models are quantities like temperature, precipitation, rain, snow, aspects of atmospheric circulation, like winds. They're sometimes quantified as geopotential height, and various aspects of radiation as well. And there are many, many other diagnostics. These are really complicated, comprehensive simulations. In particular, with regard to the land surface, climate model land models vary a lot, and there are a lot of very specific outputs that might result from land models. So if you have a question about that, I might have some insight into it, but really depends on the model structure of its land. Now, in terms of temporal resolutions, these types of models are really well validated for things like the seasonal cycle. So monthly and seasonal quantities, there are some pervasive biases we see at these timescales, but this is often the timescale people are most focused on. Diurnal cycles, on the other hand, are less well validated, but it is worth noting that they often do save some quantities up to 1 to 6 hourly resolution. So if you're interested in things like extreme precipitation, you can quantify it using output from a model like this, but you have to be careful about, how realistic is it going to be. In terms of publicly available simulations, we have the CMIP6, which basically samples across many different climate models across the world and uses both long historical and future climate projections. And we have this tool called the CESM Large Ensemble, which takes one climate model based in the US and runs many different ensemble members representing different pathways of internal variability. And so it's really good at looking at the natural variability of the climate system. Now, I just want to close by describing some ways we can take climate model data and downscale it to higher temporal and spatial resolution. So one strategy is using dynamical downscaling. So this is something like taking a regional weather model like the WRF model and basically using boundary conditions from reanalysis or a climate model to simulate at higher spatial resolutions, maybe 9 kilometers or up to 3 kilometers. A group at UCLA has been doing a lot of work on this for the Western US. And it's worth noting that, you know, if you have some bias in those boundary conditions, it's going to end up being inherited by the dynamically downscale model. And it's not like when you downscale, you fix all these biases, but you can still get information at a higher spatial resolution. For tropical cyclones in particular, which is something I'm really into, there are specialized techniques to downscale tropical cyclones. Tropical cyclones are not explicitly simulated by most GCMs, and so various groups have created these ways to create many physically plausible tropical cyclones. I don't have time to go through this in detail, but I've done a lot of work on this for the Philippines, but there are also methods for doing this for many other parts of the globe. And this is a summary of my presentation. I just want to close by saying I think climate change projection and attribution of land surface hazards is a challenging but exciting frontier for clash modeling efforts. And so I'm hoping we might be able to think creatively about this interface. Okay, so that's it for my presentation. I think we have Amir up next, if he wants to share his screen.
Can you see my screen?
Yeah, want to put, yep, that looks great. Thanks.
Great. Hello, everyone. Thanks for the invitation. I'm happy to be here with you. Today, I'll talk about compound and cascading hazard and some existing methods and frameworks for their evaluation. Let me start with a quick example. Let's consider this coastal environment. You can get flooded by the ocean. We call it ocean flooding alone, or river flooding, we call it fluvial flooding, but they can happen at the same time when there is a hurricane, or even atmospheric rivers bring rain and surge at the same time, and hurricanes too. But also direct rainfall, we call it pluvial flooding, on top of an already flooded area that can be like a third driver of local flooding. And these drivers can interact with each other, even randomly. Like, for example, an extreme high tide, king tide, can happen at the same time of an independent fluvial flooding. So what happens? The amount of water that can drain into the ocean is a function of gradient. And if flood peak is coming from left with this flood peak and ocean water level is low, water can easily drain into the ocean, low tide situation, for example. But if there is high tide situation or surge, or both at the same time, then less water can drain into the ocean. It means more backwater. In some environments under extreme situation, rivers can even go backwards and cause extreme flooding. And of course, on top of that, pluvial rainfall, like in case of Hurricane Harvey, multiple days of continuous rain in the same environment can make things a lot worse. Another interesting example was Hurricane Sandy. Not only there was rain, an extreme surge and all that, it happened at the same time of kind of high tide. So imagine all that plus a higher baseline. And with rising sea levels, it means your coastal flood risk will continue to increase, even if rain and river discharge remain the same, just because the baseline is increasing. So, but there are more complex cases. This is an example, a series of events happened over 5 years. Extreme drought ended with extreme rain, just like this year. And of course, rain creates fuel for vegetation growth, fuel for fires, and rain over burned areas can cause debris flow. So this is more complex. For the case of coastal flooding, we have even physically based models that can easily simulate these interactions. But for complex cases like this, just time adds huge complexity here. So in a recent paper, we put different types of compound and cascading models into these different categories, from multivariate to spatially compound events where space brings events together, or precondition like rain over snow or rain over burned area, and also cascading events. So we have developed several models that are available online for these types of events. For example, our NBCAT model is designed to capture the relationship between different types of events. The second one, multi-hazard scenario, generates hazard scenarios, and hazard scenarios are things that are systematically ignored. They are very important. I don't go into the details, but for all the types of events like this, you need to have a plan. But what hazards do you want to consider? There are infinite combinations for anything. For example, in a case of coastal flooding, I mentioned ocean water level, the y-axis, x-axis, fluvial flow. If you consider two events, ocean and fluvial at the same time, your hazard scenario will be like this lower one. One at the time will be the upper one. And again, there are many different combinations of events that can give you, things like this. Now, if you want to calculate return period for estimating failure probability of a coastal levee, first you need to have a hazard scenario. Without that, yeah, people have done it, but basically without a hazard scenario, that's not going to work. Anyhow, so we have used these models for different types of, they are not unique to a certain event, they're general, can be used for different hazards. For example, this is an example of global compound drought and heat wave analysis, which shows basically these compounding events is projected to intensify in the future almost everywhere. We have done attribution analysis the same way we do kind of traditional attribution, but usually attribution is one variable at a time. We have done it in multivariate space, looking at drought and heat wave and other hazards in a kind of joint interaction between the two hazards. Here are examples, like for example, the 90th percentile of drought and heat wave under pre-industrial blue versus basically historical condition. Shift to the right means more extreme compound hazard due to anthropogenic emissions. Basically, this is extracting the human component, highlighting the human component. This is the global analysis of attribution I showed you earlier, which shows these are probability ratios highlighted here, basically showing that anthropogenic emissions have significantly increased compound drought and heat waves. I'm running out of time. So these are time series of the same thing, again, highlighting the same issue. But when it comes to events like this, we have major gaps. So to address problems like this, we have developed models for empirical analysis of cascading hazards. So we have our own method where we empirically look at rain over burned areas, and we generate our own indicator of like compound hazard, which is defined in a specific case for rain over burned areas here. And we link this to, for example, natural gas pipelines in California and how that risk is going to change. But the problem is, in places like this rain over burned areas, this is exactly where a famous debris flow event happened in Santa Barbara. There are many areas with the same conditions, but failure happened in one location. And understanding why is not easy. And we are using some new bottom-up approaches, AI learning algorithms to kind of get into those cascading events. I believe I'm out of time. I stop here. I'll be happy to take any questions later. Thank you.
Great. Thank you so much, Amir. That was fantastic. Next up, we have Park Williams discussing modeling forest fire in the Western United States. Park, can you go ahead and share your screen?
Yes. 1 second. Okay. Are you seeing my slide, Jane?
Yes, looks great.
Okay, great. Amir, thanks. That was a really nice segue. If we want to be able to understand the future of extreme runoff events in the Western United States or anywhere, then wildfire and vegetation are really critical parts of the system that need to be able to be simulated. And in areas where wildfire is changing rapidly, then this is really critical. And the Western United States is one of those areas. We also are motivated to be able to simulate changes in wildfire and vegetation for other hazards, such as smoke transports and pollution. That's what's illustrated here in this satellite image of the Western United States. The reason why the Western United States is an area where I've been focusing a lot is because wildfire activity in the West has been increasing very rapidly. For the better part of a century, humans had essentially commanded control of the wildfire regime in the Western United States. And despite our strongest efforts to continue fighting fires as hard as we can every year, wildfires are increasingly escaping our control. There are a lot of proposed reasons for this, land management being one of them. As every fire that we fight successfully, we're essentially kicking the can down the road, allowing fuels to continue accumulating, and that might be contributing to this trend. But the main driver appears to be trends in climate. The climate over the last several decades has become warmer and drier, and the scatter plot is showing that the annual area burned has increased in step. The warming and drying explains, or warmth and dryness explains interannual variability in area burned very well, and also the rapid shift toward very large wildfires in the last few decades. Importantly, this relationship, it looks linear here, but that's because the y-axis is on a log scale. This is actually an exponential relationship. And so as we think about what's going to happen in the future, if we have high confidence that the atmosphere is going to continue to get warmer and drier, then we should have high confidence that we are going to continue seeing record-shattering wildfire years like 2020 into 2021. Those years could have easily been bigger than they were, and I anticipate in the next couple of decades we see years that make those years actually look pretty moderate. But you can't have a shift or you can't have this continued shift towards exponentially increasing fire sizes indefinitely, because at some point we start running out of fuels. And of course, fuels are really important for constraining the ability of climate changes to promote increasingly large wildfires. And so if we want to be able to simulate the future of fire or understand what the future of fire is going to be, it's certainly going to be a lot more complicated than just extrapolating out that simple linear relationship that I showed 2 slides ago. And so the first job that my collaborators and I have done is to develop a forest ecosystem model for the Western United States. This model operates at a 1 kilometer resolution. It's called Dynaforest. It was led by my colleague Winslow Hansen, with huge contributions from Anna Trugman and Meg Krawchuk. This model simulates 11 different forest types in the Western United States and does so dynamically. So we're actually simulating tree growth. We're simulating competition among different seed types and determining what establishes after a die-off event or a wildfire. And then alongside this model, we have developed a wildfire model. Now, this model is a statistical model. It's not process-based, and that means it's heavily parameterized. The reason is because at the scale of the Western United States, it's just not realistic to be simulating individual flames in a very process-based way. The variables that go into this model are variables such as fuel type and fuel abundance, as well as human population variables like distance to dense population centers, and of course climate variables, climate anomalies like variables like the vapor pressure deficit and precipitation, and especially the frequency of precipitation events. And so we have fuel, human, and climate variables all interacting to simulate the probability of fires and the sizes of fires. The time series I'm showing in gray are 500 different simulations of monthly area burned, and then the black is the ensemble mean. Our model simulates reality quite well here. I have forced the model 500 times with observed climate data. And in these model simulations, we are simulating the forest ecosystem responses to variations in climate as well as variations in fire activity. And then in orange is the observed record of forest fire area across the Western United States. And so you can see that during the period of overlap with good observations, the observational record is mostly based on satellite data. During that period of overlap, we do a very good job at explaining the interannual variability. We also capture the majority of the increase in area burned that's occurred. And I don't have time to show, but we also do a very good job at capturing regional variations in area burned, as well as the intra-annual, the seasonal cycle of area burned. And now, just as a teaser here, I don't have time to go into specifics, but here we did an alternate set of simulations where we forced the model over again, but in a counterfactual setting where we have removed trends in temperature, humidity, and precipitation as represented by the CMIP6 multi-model mean. And so this is meant to remove trends in climate that we think are due to human-caused climate change. In doing so, removes essentially all of the observed or all of the simulated trend in annual area burned in Western United States forests. Importantly, that effect of human-caused climate change is not spatially uniform. It's the strongest in areas that either have a lot of fuels. You need a lot of fuels in order for human-caused climate change to make a really big deal, or in places with Mediterranean type climate. So places where it rains year round, climate change has promoted larger fires, but a record-breaking hot summer isn't necessarily going to be a record-breaking fire summer because rain could come and bail out an area. And so the climatology of a region is really important as well. And with that, I will thank you very much for your time.
Awesome. Thank you so much, Park. So next up, we have Chuxuan Li from Northwestern presenting augmentation of WRF-Hydro to simulate post-fire debris flow susceptibility at regional scales. So take it away, Chuxuan.
Thank you, Jen, and thank you, everyone. Let me put it in the present mode. Can you see my screen now?
Yes, it's not in slideshow mode quite yet on our end.
Okay. Hold on a sec. How about now?
It seems to be okay. Now it looks good. Thank you.
Great, thanks. My name is Chuxuan Li. I'm a PhD candidate at Northwestern University. Today, I'm going to talk about augmentation of WRF-Hydro to simulate post-fire debris flow susceptibility at regional scales. And this study is funded by NSF. First off, an overview of WRF-Hydro. WRF-Hydro is a three-dimensional physics-based and fully distributed hydrological model. It consists of NOAA-NP land surface model that can be driven by precipitation data set to simulate evapotranspiration, soil moisture, snowpack, runoff, energy fluxes, etc. And this is two-way coupled with a high-resolution terrain routing model that simulates overland flow and subsurface flow. And this, in turn, is coupled with a channel and reservoir routing model that simulates stream flow. And WRF-Hydro is the hydrologic core of National Water Model. It outputs stream flow forecasts at about 2.7 million river reaches. The first modification we did to WRF-Hydro is to modify the source code to output overland flow at really high resolution. And the two major variables we used from this augmented version of WRF-Hydro are the overland flow and the stream flow, because post-fire debris flows are mostly runoff generated. And the second modification we did is that we changed the parameters to replicate the burn scar effects on hydrology. And here I'm showing three maps of three different parameters. And the red polygons in these maps are the wildfire burn areas from the 2020 wildfire season in Central California. To replicate the vegetation effects after a fire, we changed the land cover type within these wildfire burn areas to a burn scar analog in wildfire that's called barren and sparsely vegetated. And that will automatically reduce the canopy height and overland flow roughness, which is shown by the left two figures. And then to replicate the soil sealing effects after a fire, we reduce the saturated hydraulic connectivity within those burn areas to reduce the infiltration rates of soil. And we found that after accounting for the burn scars, our modeled stream flow fidelity significantly improves. And here I'm showing one example at a USGS stream gauge that's located downstream of a wildfire burn scar. Specifically, we're looking at stream flow discharge on the left y-axis versus time on the x-axis. And the black line is the USGS stream flow observation. The red line is the WRF-Hydro simulation after accounting for the burn scar, whereas the purple line is the one that without the burn scar. And we can see that after accounting for burn scars, we can capture the first two peak flow events much better in terms of timing and magnitude. And this is also manifested by the substantially increased Nash clip efficiency value. It increases from a negative value to a value that's approaching 1, indicating very good model performance. And this is just one example. There are more examples in the paper. So we use this USGS streamflow observations to validate our models. And after validation, we proceed to use this validated model to assess regional post-fire degree flow susceptibility. And we do that by looking at a case that occurred in January of 2021 when an atmospheric river falls on a Wi-Fi burn scar that triggered more than 4 post-fire degree flow events. And here I'm showing the accumulated precipitation in the MRMS precipitation product. Here's Pacific Ocean and here's coastline. We can see that the maximum accumulated precipitation falls within this Dolan burn scar and downstream of the Dolan burn scar. And in the middle, I'm showing the simulated peak discharge simulated by our augmented version of WRF-Hydro. And yeah, and again, the maximum peak discharge was observed within the Dolan burn scar and downstream of Dolan burn scar. And then we zoom into the Dolan burn scar to assess the post-fire degree flow susceptibility there. So the green polygon here is the Wi-Fi parameter, and the colored polygons are the susceptibility shown using a metric called normalized peak discharge. And we calculated normalized peak discharge by dividing peak discharge by the catchment area. So each of the polygons here is 1 catchment. And if it's orange to red, that means it has high to very high susceptibility level. The green triangles followed by these black arrows are the 4 observed degree flow events. They were discovered by people because they intersected with major roads, and there are many more in the remote mountains that we cannot discover. But it's shown by model there are like high to very high susceptibility level there. In general, our susceptibility model corresponds well with this limited observations of degree flow events. And to take a further step, we want to extend the capability of WRF-Hydro to do probabilistic forecast of land surface hazards. Here I'm showing an example that WRF-Hydro can be coupled with GEFS precipitation forecasts. GEFS has 30 members and it has 16 days out weather forecast. It can be used to driven WRF-Hydro, and that could produce an ensemble forecast of these susceptibility maps. And in this project, we are looking at a much larger spatial scale. It's over the entire state of California. And in addition to GEFS, WRF-Hydro can also be coupled with other precipitation data sets, for example, some short-term weather forecast data or long-term climate projections. And if other spatial temporally high-resolution precipitation data exists, WRF-Hydro can be coupled with those as well to produce susceptibility simulations at time scales that's on the order of minutes or spatial scale on the order of meters. In addition to stream flow and overland flow we used for previous studies, there are many other variables from WRF-Hydro that could be relevant for land surface hazard studies. For example, soil moisture and snow water equivalent. And it's shown by other studies that it can be coupled with sediment erosion and transfer model to simulate sediment erosion hazards. So with that, I would like to thank everybody for listening. And if you want more details, please check out our paper at this link, and I can answer questions at the end of the session. Thank you.
Great. Thank you so much, Chuxuan. That was really impressive. Next up, we have Deanna Nash from UCSD presenting modeling atmospheric rivers associated with hazards in Southeast Alaska.
Hello. All right, I'll put it in slideshow mode. You should be seeing my screen. Great. Okay, so good morning. My name is Deanna Nash. I'm a postdoctoral researcher at the Center for Western Weather and Water Extremes at University of California, San Diego. And today I'll be talking about how I integrate various models to study atmospheric rivers that are associated with hazards triggered by extreme precipitation in Southeast Alaska. So just a kind of general overview of what atmospheric rivers are. They are long, narrow bands of very intense water vapor transport in our lower atmosphere. So here I have an example, an animation showing two atmospheric rivers that made landfall in Southeast Alaska in late November and early December 2020. So the data that's plotted is reanalysis data, which is global models combined with global observations. And the green shades are our water vapor transport, or we call it IVT, which is a good indicator of the spatial and temporal extent of the atmospheric river. And then the blue, green, and red shades are precipitation. So the first atmospheric river for these two events was a fairly weak atmospheric river, so the green shades aren't as strong. It did result in some snow across the region, and it was the first snow of the season there. However, the second atmospheric river that came in was a lot stronger, a lot more moisture, and resulted, it was also very warm, and resulted in a lot of rain, flooding, and devastating landslides across the region. So floods and landslides triggered by these extreme precipitation events are fairly common in Southeast Alaska. And we do know that between 60 and 98% of extreme precipitation that occurs is associated with these atmospheric rivers. So improving our understanding and forecast capability of these different characteristics of what would make an atmospheric river more likely to produce more precipitation is really useful in increasing situational awareness before these events happen. So here I have a schematic of some different risk factors during an atmospheric river extreme precipitation event. And I'll just be focusing on the first four components, all revolving around atmospheric rivers. So we're thinking about, as that atmospheric river comes in, how much moisture it's carrying, how strong are those wind speeds, the direction that it's coming from is really important relative to topography, and then how long that atmospheric river is lasting. And then we're also going to be thinking about how much precipitation is predicted to fall, how much precipitation will accumulate, and whether that precipitation will fall as rain or snow. So we can use our weather models or our reanalysis to determine the duration, moisture content, wind speed, and direction of atmospheric rivers. However, global forecast models and reanalysis are fairly coarse resolution. The ones that I work with are typically between 25 and 55 kilometers. These do give us a really good idea of what's happening on this larger scale. So for example, I have this map showing IVT and mean sea level pressure based on a global forecast system. I believe I initialized this, on the 28th, so last Friday. And it's just forecasting this atmospheric river, that reaches Southeast Alaska, I think today or tomorrow. And I went and checked, and it's almost there. It looks just about like this today. So those are really useful kind of for those broader scale patterns, knowing when it's coming, potentially how strong it is. We can also use these global weather models to create probabilistic forecast tools that can help us determine the anticipated frequency, duration, and location of landfalling ARs. So for example, this tool is showing the probability that the IVT, or that moisture transport, will exceed a certain threshold up to a 16-day lead time. So you kind of read the plot from right to left in this case. And on the day that this forecast was initialized, there was almost a 100% probability that IVT, or moisture transport, exceeding, I think it was 150, was going to reach somewhere between 35 and 45 degrees north along the West Coast. And you can kind of see that it was maybe predicted to last about a day. But then we can also see about 4 days out that there is another high chance that high IVT values were going to be happening in that same region. So these kinds of tools, or this tool specifically, is really useful for predicting that kind of like multiple ARs in a row. Right now, this tool only extends to 55 degrees north, but fairly soon it will be extended all the way up to Southeast Alaska, about 60 degrees north. Reanalysis and global weather models, that 27 to 55 kilometer data is kind of a bit too coarse to resolve extreme precipitation events, particularly like daily, hourly precipitation. So what we do is we take our coarse data and use the regional model to dynamically downscale it to a finer horizontal resolution. So the map on the left is showing a spatial pattern of precipitation during an extreme event at Aghakouchak, Southeast Alaska, at a 4 kilometer resolution. And so then you could take this downscaled data and also we've developed some quantitative precipitation forecasts. So if you took that point, for example, at Aghakouchak and said, what is the probability precipitation will be for the next few days at this location? And we have some kind of useful tools to help us there. So for example, I guess FYI, the graphs on the left or on the right aren't necessarily for Alaska yet, but you could in the future output something like this for Aghakouchak. But this is for somewhere in Utah, and the forecast was telling us that there's almost a 100% probability of at least 0.2 inches per rain at that location. And then the fun, like very colored panel on the far right is saying what each individual ensemble member within that forecast is saying. So this is really useful in seeing, like, do all the ensemble members agree, or are there some that are just telling us something completely different? These are all really useful tools in determining the precipitation. Another useful application of our downscaled data is to provide freezing level information. And that's really useful in helping us determine the fraction of frozen precipitation that is forecast to fall, for example, in a given watershed during an atmospheric river event. So the example on the left is showing an atmospheric river event on March 10th that was forecast to see a higher fraction of rain, which is shown in the green colors compared to snow. While the event on the right was for February 21st, and this was a very, very cold event, and it was forecast to see a much higher fraction of snow, which is shown by the kind of blue colors.
Deanna,
so overall, we've run out of time. This is my summary. This is my summary. So awesome. just using all these tools together to kind of create this idea of what we can expect for impacts regarding the precipitation that's predicted to happen.
Awesome. Thank you so much. So now we'll go into Q&A, and it looks like we have about 15 minutes for that. As a reminder, if you have any additional questions, you're free to put them into the Zoom chat or also onto the Google Doc, but I'll start with some questions on the Google Doc. So maybe sort of a broad question to start, which I'm sure Amir will have opinions on, but I'm curious to hear anyone's perspective. So are there joint hazards, cascades that have been identified via modeling that seem likely but have not been observed? In other words, what are the most prominent quote unquote blind spots that models can help us understand? So maybe Amir, do you want to start addressing that, and then we can see if anyone else has thoughts?
So are you broadly talking about different types? Because considering any pair, let's say coastal flooding or drought and heat waves, there are many likely scenarios that they can interact that we may not see them in our observations. For example, if you have, let's say, 100 pairs of some observations, you can always fit a multivariate model and get an infinite combinations, and most haven't happened. But in fact, we have a method that can estimate likelihood of occurrence. In the multi-hazard scenario I showed, there was a color code. The color code is likelihood. So the way we do this kind of analysis on hazard scenarios, we assign a weight to any pair of events, and then we color code based on likelihood. So yes, we can actually statistically identify high likelihood relative to low likelihood events.
Interesting, thanks. Yeah, I mean, in my own work, something I've been thinking about recently is there's been some research on the probability of having a compound tropical cyclone heat wave event. And that's an interesting case where we're quite certain moving into the future, we'll see more and more events like that. But we actually haven't seen that many compelling examples in the historical records. So there can also be, you can assess that there's an event that could happen statistically based on the historical record, but hasn't happened yet. And likewise, there are ones that we expect might happen more in the future with global warming, but we haven't observed that much yet. Do any of the other speakers have further thoughts on that? Otherwise, I'll go to the next question.
I'll just add that really high runoff events across large watersheds is something that I think that we will see in the next decade or two, but there isn't that much observational precedence for so far. A lot of my work was actually motivated by a conversation I had with a water manager in the Department of Water Resources a few years ago. I asked, are the increasing sizes of fires really on your radar as presenting a big hazard for water management? And they said no, relative to the size of the watersheds they care about, the fires are really minuscule, even though they make the news, they're small. That was 5 years ago, and the story has changed already that quick. And so I think that it's very, in the Northern Sierra and North Coast ranges in California, well over 20% of the area has burned just in the last 7 years in the forested areas. And so the hydrology is changing rapidly, and we're very likely, I think that we can use models to understand the probability of, say, giant flooding on the American River or out of the Feather River Basin more than observations can really tell us.
Interesting. Thanks, Park. Maybe following up, there are a couple of questions regarding your presentation, and one asks, how well can we identify or model areas of high fire likelihood on an annual basis? And what's the spatial pattern of fire susceptibility? And I asked I wrote it, I know I should, but I was just wondering whether your fire modeling techniques can be used to project into the future if we just end up with too many uncertainties if we go beyond this kind of historical period.
I think I can answer both of those, and also rope in an answer to another question I saw in the Google chat at the same time. So the regional probabilities and sizes of fires are really strongly driven by cool season precipitation as well as warm season heat and aridity. So at this point in this year, we'd say the dice are loaded toward a pretty low fire activity year across a lot of the West because it was so hot. But maybe only about half of the predictive power has been accumulated so far, and the rest is really going to come down to whether or not we see really intense heat waves this summer and whether or not it rains during or after those heat waves. Last year saw intense heat waves. We're looking like it's going to be a really big area burned year, and then we had rainfall on just the right places during or after the really intense heat waves, just as the fire season was getting going, and so we really lucked out. And that's all to say that on a regional scale, in terms of forecasting annual fire activity, there's a lot of uncertainty if we can't forecast where the heat waves are going to be and how intense they're going to be. However, on this time scale of the and the most important variables for the warm season are really the warm season relative humidity and vapor pressure deficit. Forecasting into the future, though, we get around the need to be able to forecast seasonal meteorology, and we have pretty high confidence that it's going to continue getting warmer, that warm seasons are going to continue to have more intense heat waves. And I do think that we can simulate fire, say, on the time scale of the next 30 years across the Western United States If we have an idea of how climate's going to change, then I think that we can actually do a pretty good job at simulating the continuation of fire trends and how and when vegetation feedbacks might start causing the fire response to area burn to start leveling off because of fuel limitations.
Interesting. Thank you. So maybe we'll do a question for Chuxuan next. So I asked this question. I'm happy to take any other questions from the audience about her presentation, but I'm just curious, is there widespread data on burn scars such that the modeling techniques with WRF-Hydro you mentioned can be applied for many locations? My understanding, when you do the risk analysis or the post-fire susceptibility analysis, are you basically making an assumption that you have a burn scar in a given location? But what does the actual observed data look like for burn scars right now?
Yeah, so actually the burn scar data I input into WRF-Hydro is actually observation-based burn parameters. And that comes from like many sources compile burn scar parameters or burn severity data. For example, the MTBS, which is monitoring trends in burn severity. That one is over the entire United States. They provide burn parameters in addition to burn severity data. And also other governmental agencies like CAL FIRE will also compile burn info. And we also like partition them into like if it's wildfire or it's prescribed fire, that sort of thing. And over a global scale, there is NASA's MODIS data available. So yeah, WRF-Hydro can deal with all sorts of format as long as you put them into like a netcdf file format that WRF-Hydro can work with. Then yeah, there are many data sources there.
And typically, how long after an event does that burn scar information become available? Like, is this something we can use sort of after the fact, but when an event is underway, we probably don't have the burn scar information available yet?
Yeah, so that's a good question. So for MTBS, they have pretty updated data. So right now, the most updated one is from the 2022 to burn season. And in terms of MODIS, I think there might be a lag, but NASA right now is putting together more like a real-time forecast of burn situation. They call it DIST program. And that one is like sort of combining remote sensing techniques to monitor the burn situation out there. So it's quite like real time. Yeah.
Interesting. Thanks.
Thank
so
you.
Maybe, yeah, maybe we'll go to a question for Deanna next. So there are a couple questions for you under general questions / comments. One is, are there unexpected or counterintuitive predictions for rainfall? In other words, have the models identified outcomes that reveal interesting or new dynamic interactions with the land and atmosphere? So that's one question. And then another question, which is maybe semi-related, is for the dynamically downscaled model runs. Can you identify specific processes within the atmospheric rivers that drive high intensity precipitation, such as enhanced orographic flow, convective instabilities, et cetera? So if you have thoughts on either of those, that would be great.
Yeah, so I guess probably start with the second one. It's a little easier. The answer is definitely yes. There are specific processes that we can see in those models that are driving higher precipitation. So I guess a thing to keep in mind is like not all atmospheric rivers result in precipitation, and then definitely not all atmospheric rivers result in extreme precipitation. So we've been able to see that, for example, the direction of the oncoming AR relative to the topography is really important for enhancing that orographic flow. So if it's perpendicular to the topography, you're more likely to see that higher extreme precipitation in mountainous regions. Convective instabilities, I don't really have most of my experiences in like wintertime precipitation. So convective instabilities aren't really happening, but there are a couple other processes like mesoscale frontal waves, which is just the intensification of the cold front that's happening that can really enhance precipitation. We saw that in California this past winter, that the atmospheric rivers that came in and had those mesoscale frontal waves definitely resulted in higher precipitation. Narrow cold front rain bands, that was the case with the atmospheric river, with the very weak atmospheric river that came in and resulted in the Montecito debris flows, was associated with that narrow cold frontal rain band. And then for unexpected or counterintuitive predictions, I mean, I think there's always that space in rainfall prediction for counterintuitive and unexpected rainfall prediction, but definitely having the higher or the finer scale resolution data is useful for revealing those more interesting dynamic interactions for sure.
Great, thanks so much, Deanna. I know Amir has to hop off right at 11, so maybe I'll just ask you a question to clarify the tools you discussed for looking at compound hazards. Are they designed to look at compound hazards if you have data in the same location? And also, what types of kind of temporal or spatial resolutions are appropriate for applying those modeling techniques to? Like, basically, how flexible are the tools for the types of inputs that can be provided?
So we try to design them in a general way so they can be used for different hazards, different scales. They don't have to be at the same exact location, but basically they are designed for events that have some kind of relationship, and this relationship can be somehow quantified. So in case of, for example, coastal flooding or drought and heat waves, these are examples where you can, or fires and heat waves, or fires, heat waves, drought. These are types of events that you can quantify the relationship. So it works broadly for those types of events. Of course, for some specific project, it may not work, or some other, but it's broadly designed for capturing the relationship and quantifying the relationship between events. But when you have, for example, rain over burned area, and rain can happen like 6 months after your fire, the events can be climatologically independent from each other in some cases, then those methods won't work.
Okay, interesting. So it's designed to deal with situations where you have some joint probability between the two events.
Right. When the events are independent, we use a kind of empirical approach, like the rain over burned area I showed is more like an empirical approach. Still, we design a kind of metric can define that compound event, but the analysis is empirical.
Okay. Okay, great. Cool. So I think we are basically out of time. I want to thank all the speakers in this session again. This is really, I'm impressed by how much ground we managed to cover, and I'm excited to see what ideas this generates about coupling climate to land surface hazards. So thank you so much, everyone. That was wonderful.
Thanks, everyone.
Thank you. Thank you, Jane.
Thank you, Jane. Thank you, speakers. Clearly,